Alright everybody, welcome to COVID Calculus number 3. In this case we are minimizing the area of a triangle given a constraint. So this is going to be a little bit in depth, but what we have is a triangle, it's a right triangle whose legs lie on the x and y axis, and it has to cross the point 2, 5. So normally when you think of areas of triangles, you're talking about a base and you're talking about a height. The area itself is going to equal 1/2 base times height. And normally you're given some perimeter value, and the base and height kind of move inversely. So if the base gets bigger, the height gets smaller, and vice versa. So you normally have something like this. And I did this graph in the other two videos, but it was slightly different. I have a base value, and given the base, the area will change. If the base is really, really tiny, the area will be really, really tiny. What that means is this. I have this really skinny triangle, right? Let's say it's 1 and 10, something like that. And if the base is really, really big, the area, again, is really, really tiny. And again, let's say it's 1 and 10. They just kind of flip-flop. And then in between, you have something like this, and this becomes a little bit more mid-ground, but the area becomes much bigger. So this 1/2 base times height, this would be 5, this would be 5, and this would be 7 times 6 is 42, divided by 2 is 21. So you wind up getting a graph that looks like this. And somewhere in the middle here, where the base is kind of in the middle ground, you have a maximum value. But in this case, we don't have a limit on the perimeter. We have a constraint in where the hypotenuse can pass through. So it looks a little different. So what we have is, let me go ahead and redraw everything over here. We have a point on an x and y axis right here. That's 2, 5. And if I make the base really, 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 really tiny, well, this is 2, 5, so it has to be bigger than 2. And here's 5, and that has to be bigger than 5, right? So I could draw a line that's almost flat, and it kind of comes, and it makes this really long triangle going that way, right? And that has a fairly large area. Or I could do it going the up direction, right? These are kind of the two extremes. And again, you have this almost infinitely tall triangle going up, and either way, you get a graph that looks like this. Well, first off, it has a constraint at 2. So the base can't be smaller than 2. And the area at 2, when it's right at 2, the area is actually quite large. And then if I just go infinitely large over this way, where the base gets really, really, really long, and the height is essentially shrinking down, closer and closer and closer to 5, the area again is really, really big. But if I draw something kind of in the middle, something like that, the area shrinks drastically. So you wind up getting a minimum value, and it's some value here. And that value has a slope at that point of 0, or where the derivative of a equals 0. Okay, so we're looking for that minimum, and because of that constraint, that kind of tweaks what we're thinking. So we have this as our area formula, and we're trying to minimize that. We're going to try to do the derivative of that, but again, just as previously, we have this second variable, and we want to get rid of that. So what we have, the handy dandy, because of this point, we have this box here, where this value is 2 and this value is 5. And what that gives us, when we take out that box, is one big triangle, which is our main triangle we're thinking about, and 2 small triangles, one there and one here. Well, both of those triangles are similar. We know that because they're 90 degrees, they're passed by this parallel line, and they share angles. This angle in the small one is the same as the angle in the big one. This angle in the small one is the same as the angle in the big one. So they share angles, which means that third angle, 90 degree plus the same angle, means that third angle and this third angle, again, are equal. So they're actually similar triangles. I'm going to go ahead and pull them out. And what we have is our original triangle right here. It has some base, we don't know what it is, and it has some height. And it has some hypotenuse. I'm going to call that C1. You don't need to have that, but we're going to call it that. And then we have a similar triangle, which is smaller than that. And we don't know the base, but if we come up here, we know that this value right here, so that base is the entire base minus 2. The 2 is this remainder here. So I can just say base minus 2. And I also know that this height right here of this triangle is 5. So I can put that in. So I have two kind of hinting values there, and then I have C2. I'll call it, again, we won't need that, but we'll throw it in there. So what I can do is a ratio, and I can say the ratio of the heights, h to 5, is the same as the ratio of the bases, and make sure that I have them in the right order. The big height and the big base are on top, and the little height and the little base are on bottom. Well, I'm solving for h, so I can multiply by 5, and I get h equals 5 base times base minus 2, right? So now I have something to plug into my area formula, where every variable now will be b's. So let's go ahead and do that. So I'm going to rewrite my area formula, 1/2 base, and then I have height, but instead of height I'm going to put 5b over b minus 2, right? Okay, again, if we go up to our graph, I'm looking for a prime equals 0. So I'm going to have to take the derivative, and I'm going to have to set it to 0. Before I do that, I'm going to simplify this. So I'm going to say a equals, the b goes to the top, 5b squared. The 2 goes to the bottom, 2b minus 4, right? 2 times b, 2 times 2. This is my final area formula, okay? But I want the derivative. So the derivative of this, I have a b in the top and a b in the bottom. This is going to be the quotient rule. The quotient rule is f prime x g x minus f x g prime x over g x squared, right? What this means is I have basically f of x over g of x. My 5b squared is my f of x. Here I take the derivative of it, and I multiply it by the denominator, or 2b minus 4. Then I take the numerator, multiply by the derivative of the denominator. Then I divide everything by the denominator squared. Okay, so let's go ahead and do that. So first, I got to take the derivative of the numerator, right? Take the 2 down, it becomes 10b. And multiply that by the denominator, 2b minus 4. Then I subtract the numerator times the derivative of the denominator, which would just be 2. And I put that all over 2b minus 4 squared. Okay? All is well and good. Let's simplify this out, and we get a prime equals 10b times 2b is 20b squared. 10b minus 4, or times negative 4, is minus 40b. Minus 5b squared times 2 is 10b squared over 2b minus 4 squared. I'm still leaving that as it is, so I don't want to have to multiply it out if I don't have to. I'm going to set this all equal to 0, because if we go back up here, I am looking for this minimum point right here, and that is where a prime equals 0. So let's find that. Okay, so 0 equals the 20b squared and the 10b squared can add together to be equal 10b squared minus 40b over 2b minus 4 squared. I'm going to take a risk here, and I'm going to guess that nothing in the denominator equal to 0 will be passable, because you can't divide by 0 unless the numerator is also equal to 0 at that point. I'm going to take a wild guess and assume it's not. So I'm going to, again, take a risk. You may actually want to test that, but I'm going to risk it and just get rid of it. By getting rid of it, I mean I'm going to multiply both sides by it, and multiplying 0 by that will just be 0. So I can just take that out. So 0 equals 10b squared minus 40b. All right, I'm getting really close. I can divide both sides by 10. 0 divided by 10 is just 0. I get b squared minus 4b. I can take out a b. b times b minus 4. Well, I have two options here. If b equals 0, I would have 0 times 0 minus 4, which would be 0. So 0 works. And if this parentheses equals 0, so I'd have to have 4 minus 4 equals 0. B could also be 4, right? So I got two options to choose from. But we got to remember, let's come back up here. We happen to know that my base can't be smaller than 2, right? This base cannot pass this line. It has to be on this side. So it can't be 0. 0's over here. So the only other option is that b would equal to 4. So I can go ahead and cross that out. And I can say my base has to equal 4. If that's the case, let's go ahead and find our formula here. Excuse me, our area here. So I happen to know that the area equals 5b squared over 2b minus 4. b equals 4. So let's plug this in. Area equals 5 times b squared. So it was 16 times 5. I actually don't know what that is offhand. 30, 80. Okay, so we have 80 over, we have 2b, so 2 times 4 is 8, minus 4 is 4. 80 divided by 4 equals 20. So our area is 20. And it's units. It doesn't give any, right? It's just x units. Okay, so what we've done, let's go ahead and move out. Oop, not that far. We started with some unknown value, right? We happen to know that it had to cross through this one point. We didn't know either side, but we knew a portion of those sides. We also knew that it wasn't kind of this standard triangle area calculation graph. You know, we knew that the height and the base were not tied to one another. It was simply this point that it had to cross through, which meant that we were looking for something that looked like this. There was some minimum value where the slope would be equal to 0. We also knew that that minimum value had to be greater than 2, right? So in this case it was right here, and it was equal to 4. Then what we found out is because of these kind of the square that's able to be taken out of this triangle, we can create similar triangles right here, right? Here are similar triangles. The similar triangles allow us to do a ratio, the ratio of the height to the other height and the base to the other base. And that allows us to solve for h in terms of b. When we do that, we can then plug the substituted value for h into the area formula, and we can find the derivative of that. We did the quotient rule to find the derivative, and eventually got down to here, where we plugged in 0 for the derivative and solved for b. b gave us two values, one of which did not satisfy our criteria that it had to be larger than 2. So we're left with only one value. Once we have that value, we can plug it into the area formula, and you get your area. All right. Well, I hope that was useful. And again, as COVID ticks along, I'll keep posting up random calculus videos. Hope that's enjoyable, and hope it taught you something.